Hello everyone, welcome to ECE 6520. Today is our lecture number 19. Okay, so today we're going to talk about our homework 3. Okay, so we're going to go through the problem one by one. Okay, so let's see the first question. So the first question is called pre-processing the output, right? So this basically means that we consider a communication channel, right, which obviously is a DMC, right? And the channel is characterized by this transition probability, okay? And so what we're going to do here is that we're going to pre-process the output Y, right? And then the statistician claims that this will strictly improve capacity, right? And so what we're going to do is that first we're going to show he is wrong, and secondly we're going to see under what conditions does he not strictly decrease capacity. Okay, so let's take a look at this question. Okay, first of all, so what we get here is that we know y tilde is equal to g of y. Okay, and clearly from here we can see that x to y tilde, so this forms a Markov chain, right? Okay, and given that, so obviously what should we consider is the data processing inequality, right? So by the data processing inequality, okay, we can get, so the mutual information between x and y should be bigger than or equal to the mutual information between x and y tilde. Okay, so this is okay, but so we're not done yet, right? So it doesn't mean the capacity, it doesn't mean the mutual information. I mean the capacity between x and y is bigger than capacity between y and y tilde, right? So we need to one more step here, okay? Because the capacity is defined as a maximization over all the possible input distributions, right? So what we're going to do is that we let px star be the distribution of x maximizing the mutual information between x and y tilde. Okay, right? You're going to see why we want to assume that, right? So given that, then we can obtain that the capacity of the original channel, which is given by this, right? So now what we're going to do is that we let px equals to p star x, right? Therefore, since so p star x may not be the maximization of this mutual information, right? Therefore, we can get that this guy is bigger than or equal to the mutual information between x and y when px equals to px star. Okay? Okay, great. And now let's fix px star, right? Because that this guy is bigger than or equal to this guy, right? Therefore, we can get this is bigger than or equal to I mutual information between x and y tilde given px equals to px star. Okay, and let's recall. So we assume that this is the distribution of x that to maximize this guy, right? Therefore, it basically means that this equals to the capacity between x and y tilde, right? So now what we have shown here is that c is bigger than or equal to c tilde. Okay, then we can see. Now we prove that. Let's see. We prove that the statistician is wrong, right? So pre-processing cannot increase the capacity. Okay, very good. Okay, so this is part A. Now let's see the part B. So for part B, I ask you to see under what condition. So this preprocessing does not strictly decrease the capacity, right? This again, so it's a data processing inequality, right? So I have to go back to the proof of the data processing inequality to see where this equal sign will hold. Okay, so if we recall, so let's see. So we can write the mutual information between x and y tilde in two ways, right? This is how we prove data processing inequality. Right? One way is to use the chain rule of mutual information to write that in this way, right? And the other way to write it is the mutual information between x and y plus mutual information between x and y tilde and the given y. Okay, because this is a Markov chain, right? So given y, x and y tilde will be independent. Therefore, this guy will become 0. Okay, and that's how we prove that this guy is bigger than this guy, right? So now we need to make these two guys equal, right? Therefore, the condition is that this will be equal to 0, right? Therefore, what we're gonna get is that hence if c equals to c tilde, then our requirement is that this guy has to be equal to 0. Okay, what does it mean? Right, given y tilde, x and y are independent, right? This basically means that for x to y tilde to y, that forms a Markov chain, right? Okay, so then they will be equal, right? Therefore, so this is basically the condition, okay? So, very good. So this is the first question. So now let's see the second one. Second is question 7.2, additive noise channel. So here we need to find capacity of the following discrete memoryless channel, so which is given by this, right? And the tricky part here is that the distribution of the noise depends on the value of A, right? And we'll assume that it's binary for the input, x is 0, 1, and z is independent of x, right? Okay, so now let's compute the capacity of this channel. Okay, so this is 7.2. Okay, so in this case, we need to consider different values of A, right? Let's write it down here. So basically, we have x, then we add z here, and then output is y. Okay, and x take values from 0, 1. Okay, so obviously the capacity will depend on so the output of y here, right? So we can see what are the possibilities for the values of z, right? So z will take value from 0 and a. Okay, so the easiest case to consider is that what if a is 0 as well, right? If a is 0, then x and y would be identical, right? That is definitely a special case. Right? The first case we consider here is that if a is 0, and then in this case, y equals to x, right? So if we want to draw the channel here as what we do in class, so we're gonna do something like that, right? With probability 1, and from 1 to 1 with probability 1. Okay, this will be the channel, right? In this case, so remember that. So what we consider here is a DMC channel, right? For all the DMC channel, we have shown the capacity, which is given by this formula. Right, so now the only thing left is to compute this formula under this condition, right, under this channel. Okay, so what we're going to do is like this. So h, let's say, so I have two ways to expand it, hx or hy, right? Either way should work in general. Okay, and now clearly this guy is 0 because y and x are equal. If we know y, there's no any uncertainty of x. Hence, this is what we're getting. Okay, and so now remember that X is binary, right? So now I want to see what is the optimal distribution of X such that the entropy is maximized, right? Obviously, so this will achieve what? 1, right? 1 bit. So when X is a uniform distribution, okay, between 0 and 1. Okay, so then, so we find the capacity of this channel, right? Okay, so this is the first case. So now let's see the second case. Okay, so the second case is basically that, so now when A is 0, then there's only 2 possibilities for the output, right? As we said, the capacitor depends on, you know, the number of outputs here, right? So I said if A is 1, then we can have 0, 1, and 2, right? And if A is -1, then we can have -1, -1, 0, and 1, right? They're all 3 kinds of outputs. But if A is not 1 or -1, if A, for example, is 2, then the output could be 0, 1, 2, 3, right? There are 4 kinds of output, right? That clear? So now, when you consider all of this separately, okay, so let's see. So here we consider the case where A is 1. Okay, let's see what we're gonna get, right? In this case, so we have this formula, right? So now let's draw the channel here again. Okay, so if A is 1, then so from 0 we can go to 0, and obviously from 0 we can go to 1, right? If Z is 1, right? Then let's say from 1 we can go to 1, okay, if Z is 0, and also from 1 we can go to 2 if Z is 1. Okay, so that's basically our channel. Okay, and remember that from the problem we know, so the probability distribution of Z is uniform. Okay, it's half. Therefore, in this case, we can get it's all half for the transition probability here. Okay, okay. So given that, by observing this channel, what did you see? Okay, so this is sort of like the BEC channel, right? So this is like similar to BEC channel. Okay, so with that said, actually the capacity of this guy, if you use the identical approach to compute the mutual information, then you're going to see that the capacity of this guy will be identical at the BEC channel, which is equals to 1 minus what, half, right? So that equals to half bit. Okay, and that can be done quite easily. Okay, and the next case is that, again, as we said, so now we have 3 outputs, right? 3 possibilities for the output. So another value of A to have 3 possibilities for the output is where A is -1. Okay, so let's consider this case when A is -1. Okay, again, so this is Y. Right, in this case, what we can have is that from 0 we can go to -1 when Z is -1, right? From 0 we can go to 0, right? And let's say from 1, obviously, we can go to 1. And now from 1, we can also go to 0. Okay? And because Z is uniformly distributed, therefore, so the channel is like this. Okay? Again, so this is similar, also similar to BEC, and it's similar to 2, right? Therefore, we can also get, in this case, C equals to 1 minus half equals to half bit, right? So the computation here is almost identical as what we do for the BEC, right? If you don't recall, please take a look at our lecture notes. Okay, very good. Okay, so next is the rest, right? So let's say because we have 2 possibilities for the input and 2 possibilities for the output. right? So what is the what is the maximum number of possibilities for the total output? Right, it's 4, right? Actually, for the rest of the cases, so we can have 4 different kinds of output, 4 possibilities, right? Let's say if a is not 0 and a is not equals to plus or minus 1, right? And then we can see that if x is 0, so now what we can get is 0 and a, right, with half probability, okay? And when x is 1, so we can get here is 1 and 1 plus a again, so those are half probability, right? And 0, a, 1, and 1 plus a, they cannot equal. We have 4 kinds of output here, okay? And now let's compute the capacity in this case. Okay, so in this case, so this equals to, again, so we can write definition of the mutual information. Okay, so now let's be careful here. So what is this guy? Given y, what is x? What is the entropy of x? Now let's say if y is 0, then we know x is 0. Right? X cannot be 1. If x is a, again, if y is a, again, we know x is 0, right? So they are kind of separated, like, you know, this noisy typewriter problem, okay? So actually we can get 0 error here, okay, in this channel, right? This means that this guy is 0, exactly, okay? So now the rest of the problem is easy, right? So we have this, and clearly the maximization of this guy would be 1 bit, right? Because we can let x to be a uniform distribution over 0 and 1, okay? And we're done for the first question, okay? Oh, the second question, okay? Next, let's take a look at our third problem, okay, which is 7.3. So in this problem, it's called channels with memory higher capacity, okay? So let's see, so now we consider a binary symmetric channel, yi equals to xi plus zi, and where this plus sign is modulo 2 addition, and both xi and yi are binary, right? And we suppose that z has a constant marginal probability, so that the probability of di equals to 1 is p, and equals to 1 minus the probability that di is 0, okay? But here, the important assumption is that so z1 and z2 up to zn are not necessarily independent, right? So assume zn is independent of the input, right? And let this guy, and then we're going to show that this mutual information is bigger than nc, right? So if we derive, you know, we use a converse approach to derive it, so we can see that, so this would be basically the capacity of this kind of channel, right? Okay, so now let's try to solve this problem. Okay, so this is 7.3, okay, and here, so let's compute it. So basically, the only thing we need to do is that we want to compute this mutual information, x1 to xn, and y1 to yn. So I want to show this mutual information is bigger than or equal to n times c, right? Let's see how we can do this. Okay, so basically, again, if we see mutual information, the first step would be nothing but to write it separately, right? So in this case, so we're going to do it in this way, and you're going to see why it's easier to do it in this way. Okay. All right. Okay. So next step is that we know that yn equals to xn plus zn, right? It's modulo 2 operation. Okay, and we have seen this guy many times, right? So this can be easily, we can easily show that this guy, because we know xn here, right? Then all the uncertainty would be on zn, right? That's intuition, but we can show that rigorously, very easily, and we have done that before, right? So this guy will equal to that. Okay. So again, one intuitive explanation is that if we know xn, right, and we not know xn, we can just subtract xn, and then all the uncertainty comes from Zn. Okay, so now if we see this joint entropy, right, one natural idea to do is to use the chain rule, right? And another way to think about this problem is that we can use the independence bound of entropy, right? Therefore, so we know this guy would be upper bounded by the summation of each individual term, right? Therefore, we have because we have a negative sign, so then it's larger than or equal to a summation of this guy. Okay, very good. The next step is that we would like to make sure yn is a uniformly distributed, right? Because we need to get this n term there. Okay, so let's say this equals to n minus summation of this. Okay, so this equality sign will hold only when yn is uniformly distributed, right? Can we achieve that? So it should not be very hard, right? So this will be achieved by if we choose xn to be uniformly distributed. Okay, and you can double check, verify that. It's quite easy to see that. Okay, and the entropy of Z is known, right? It's just a binary entropy, right? Therefore, what we get here is that n minus n times hp 1 minus p, so which is given by the problem, right? So basically that is this notation. Okay, and okay, so next is that this equals to n 1 minus, okay, and that is obviously equals to n times c. Okay, and now we're done. I will prove that this guy is bigger than or equal to n times c. Okay, all right, so yeah, and so one thing to be careful here is that, so from this step to this step is kind of critical, right? And here we need to see how to make sure yn can be uniformly distributed, right? That is under the condition that xn is uniformly distributed, right? Okay, great. So next, let's see our next question. The next question is again to compute the capacity. So now consider DMC y equals to x plus z. So now the plus is a modulo of 11 instead of 2, right? And here is the distribution of z, right? So this basically means that there are 3 values of z, 1, 2, and 3, right? And the probability of each of these values is 1/3. Okay, so now we assume z is independent of x, right? So this is a very common assumption, right? Which means that the noise is independent of the input, right? So now we need to find the capacity and B, what is maximizing P star x here, okay? So let's see how we can solve this problem. So this is our question, 7.4. Okay, so now let's just compute the capacity here, right? So again, so maybe we write this, and this is mod 11 plus, right? And the distribution of z is that the probability that d is 1 is 1/3. Right, so now, again, this is DMC, right? Capacity is nothing but this guy. Okay, again, the left here is to compute it. Okay, so normally if I have this addition there, so usually write that in this way would be easier due to the fact that the second term can be simply written as z here. Okay, because y equals to x plus z. All right, okay, here, so before further proceeding, so we need to compute this guy, right? Let's do that. So this h of d is a ternary random variable, right? So if you want to compute the, so let's denote this guy as, let's say pz, right? Or let's say just denote this as p1 for simplicity. So this is p2, this is p3, okay? So here, basically, what we get here is something like this, okay? And next, so this, so we just plug everything in, so we can get okay, and so clearly everything is 1/3 here, right? This guy equals to basically this times 3, so that equals to log 3. Okay, so that's the entropy of Z. Okay, with that said, so we can write this as the maximization over Px, entropy of Y minus log 3. Okay, so next, so it's very similar to the previous case, right? So what we're going to do is that we're going to pick Px such that we want to make sure that the entropy of Y is a uniform distribution, right? Again, so this will be achieved when we pick X to be a uniform distribution, right? So if we say, so I want to make sure that Y is a uniform distribution over 0, 1, up to 10, right? So this will be achieved by choosing X to be uniform between 0, 1, and 0, and 10, okay? Therefore, with that said, so that will be equals to log 11 minus log 3, that equals to log 11 over 3. Okay, so this is for both A and B, and we clearly see that this will be achieved by this guy, right? This is basically Px star. Okay, so that will be this problem. Next, let's take a look at problem number 7.5. Okay, so this problem is called using two channels at once. So we consider two DMC channels, this and this, with capacity C1, C2 respectively. A new channel look like this, right? You can see that it's kind of product of these two channels, right? And it's formed in which X1 in this and X2 in this are simultaneously result in Y1 and Y2. Okay, so now we need to find the capacity of this channel. Okay, so before proceeding, we may think about, what should be the capacity of this channel, right? So intuitively, because so Y1 only depends on X1 and Y2 only depends on X2, right? So this may tells you that, so the overall capacity may be the summation of each of them individually, right? Let's verify whether our intuition is true or not, okay? So basically, in this case, we consider a DMC channel and it look like this. And so the transition probability should be, so if there's no any constraint, it should be something like this, right? But now we know this equals to Py given X1 times Py2 given X2, right? So Y1 only depends on X1 and the Y2 only depends on X2, right? The output alphabet is something like this, okay? So this is our channel. And now the only thing we need to compute is the capacity, right? So this is equals to the follows. So now instead of a single variable, have a random vector, right? And we can consider X1, X2 together as a big random variable, right? So the capacity of this channel should be given by this. Okay, very good. Now we need to compute it, right? So okay, again, so we need to write it down as a difference between two entropies. Okay, So let's do it this way. Okay, okay, and the next the next step is that we may want to break the entropy term. Okay, break the second term, right? Because we know the relation between x1, y1, y2, and x1, x2. Okay, let's keep the first term here. Okay, and then so we can using the chain rule, we can write this as hy1 given x1, x2 minus hy2 given x1, x2, and y1. All right, okay. Then next step is that using this condition, right? So y1 only depends on x1 and y2 only depends on x2. Therefore, so this entropy equals to y1 given x1 minus the entropy y2 given x2. Okay, okay, very good. And okay, so remember that. So our intuition tells us that this should be equals to C1 plus C2. Okay, so now we have something like this, which is good, right? The next thing we want to have is y1, hy1 and the hy2 individually, right? So here, so clearly this is less than or equal to. So if we break this into these two terms, okay, and later on we're gonna see how to make this equality holds, right? Clearly, in order to make this equality holds, the only thing we need is y1 and y2 are independent, right? Pick x, the distribution of x1, x2 to make sure that they're independent, right? Let's see how we're gonna do that later. So, okay. Okay, and if we write this, now it's clear that, right? So this and that, so this will become a mutual information between x1 and y1, and this guy and this guy will become the mutual information between x2 and y2. Okay, therefore this equals to maximize the mutual information between x1, y1 plus x2, y2. Okay, great. Okay, and in order to separate it into C1, C2, then we need to separate these two guys, right? So clearly that will be less than or equal to right? The reason it is less than or equal to is because that the same distribution may not maximize each term individually, right? But clearly we're gonna see, so this can actually hold with the equality, okay? And then this is equals to C1 plus C2, okay? And now, in order to see y C1 equals to C1 plus C2, then we need to make sure that, let's see, we need to make sure that the two inequality should be equality, right? This and that should be equality, right? And we can see that it turned out, so let's write this again. So this equality holds if and only if y1 and y2 are independent, okay? And this equality holds when what? So remember, so the first term is a function of x1 and y1, right? The distribution of x1 and y1. And second function, second mutual information, is a function of the distribution between x2 and y2, right? Therefore, it means that if this distribution is, so x1 and x2 are independent, then this will hold, right? Because this guy is just optimize it over x1, and this is optimize it over x2, right? Therefore, we can say if px1, x2 equals to px1, px2, right? Then, okay, this is actually this guy, and this is actually this guy, okay? And also because of this relationship, right? If x1 and x2 are not dependent on each other, and then y1 and y2 will also be independent. Okay, actually, from here we can actually obtain that. Okay, therefore, so now we can see this, and this equals to C1 plus C2, and our condition is if and only if. Now let's change back our color. If and only if the optimal distribution equals to px1 star and px2 star. Okay, and that's problem 7.5. Okay, so next, let's take a look at our next problem. So which is problem 7.7. So this is a cascade of binary symmetric channel, right? So we have a sequence of binary symmetric channel there, and so each has an error probability of p, okay? And it claims that this is equivalent to a single BEC channel with probability this one, and hence the limit of this mutual information is 0 if p is not 0 and 1, okay? No encoding or decoding takes place at the intermediate terminals x1 to xn-1. Thus, the capacity of cascade tends to 0. Okay, so let's see whether it's true or not. Okay, so here, firstly, we need to write down the transition probability of the channel. Okay, so this is this one. Okay, for each BSC. Okay, and we know that, so every time when the input signal pass through the channel, right? So the output distribution will be nothing but the input multiply this p, right? Something like this, x multiply p. So that will become, let's see the notation here, x1, right? That becomes x1, right? And x1 multiply p again, so that will becomes the distribution of, yeah, maybe I should use some other notation. Let's assume this is like P0, then here's P1. So P0 basically means the distribution of X0, this guy, right? And P1 is a distribution of X1. So then P1 times P equals to P2, and so on, right? So in other words, so this basically means that in the end, Pn will equals to P0 multiply P to the power of n. Okay, then, so this basically means that Pn equals to P0 times 1 minus P, P 1 minus P to the power of n. Now let's compute this guy, right? This is the hard one to compute, okay? And so normally when we want to compute this matrix to the power of something, so what we do is that we want to compute the eigenvalue decomposition of this matrix if it exists, right? Because that can simplify our life quite a bit, right? So let's see. So actually, the eigenvalue decomposition of this guy is quite easily to be computed. Okay, it turns out that this equals to this guy, right? So we need the 3 matrix multiplication here, and the eigenvalue here is 1 and 1 minus 2p, and the eigenvectors here are like this. So we normalize it. Okay, and another nice thing here is that P is symmetric, right? Therefore, Therefore, the inverse of the eigenvector matrix is just the transpose of it, the transpose, right? Okay, very good. And okay, so given this, so the next thing here is that, so now when we multiply all the matrices together, so this eigenvector matrix can be cancelled, right? Because they are order normal to each other, right? Okay, so now this means that if we compute this one, so this will be nothing but we keep the eigenvector here, okay? And inside is 1 to the power of n and 1 minus 2p to the power of n, okay? Okay, very good. And now we can easily compute this, right? That is equals to this guy. Okay? Okay, very good. Okay, with that said, so now what we want is that we want n goes to infinity and see what the distribution will become, right? So, yeah. So let n goes to infinity, and then, so what we're going to get is that, so remember, so see here, so this guy will be less than 1, right? If n goes to infinity, all of those terms will be disappeared, right? Therefore, this will becomes a uniform matrix, right? Okay, and the condition on that is that p cannot be 0 or 1, right? If p is 0, then this is 1, so it will be not true. If p is 1, then this term will be 0, right? That will be not true either, right? The condition of this is that p does not equals to 0 and p does not equals to 1. Okay? Yeah, because when p is 0, this is 1. When p is 1, this is minus 1. Right? So that will not converge. Okay, so that will be the condition here. Okay, with that said, so now what we get is the stationary distribution of this guy when n goes to infinity is nothing but a uniform distribution, right? Because we have this. Okay, very good. And from here, we can actually derive that when n goes to infinity, so the mutual information between x0 and xn will be nothing but this guy minus xn given x naught, right? And here, as we said before, because this matrix is a uniform matrix, right? So the meaning of this is that no matter what distribution of the input, the output will be a uniform distribution, right? This means that xn and x0, so they are independent, right? Then this will be nothing, and also xn is a uniform distribution. This will be nothing but 1 minus 1 equal to 0. Okay, and that will be the answer of this question. Okay, next let's take a look at next problem, which is problem 7.8. So for this problem, we want to compute the capacity of the Z channel, which is given by this guy, and also find the corresponding input probability distribution, right? So let's get started. Okay, 7.8. Okay, so the Z channel in this case is given by it's given by something like that, right? So I'll have we have a 0 here. Let's see, and so it's something like that. Okay, and the probability here's 1, here's half, and here's half. Okay, and so we know the condition of the input probability for to achieve the capacity is given by this formula, right? This is what we derived in class, right? The approach to derive it is given by our lecture notes, right? You can take a look at how did we derive this, okay? And okay, so given this, so now let's write it down here and solve it, okay? So here what we get before is that, so this guy 1 minus epsilon equals to p plus epsilon 1 minus p over 1 minus p minus epsilon 1 minus p. Okay, so here be careful here, definition of p is that, so the probability that x equal to 0, so this is p, and the probability that x equals to 1, so this is 1 minus p. Okay, so this is what we get before, and given that, since now the transition probability here is half and here is half as well, so this basically means that the epsilon equals to half, right? And given that, so we can compute this as follows, right? And if it's a uniform distribution for epsilon, right? Therefore, this is basically 1, right? So, and then 1 minus half equals to p plus half 1 minus p over 1 minus p, 1 minus epsilon, 1 minus epsilon is half, 1 minus p, right? Okay, so now let's compute it. So this equals to, the left-hand side is 4, right? 1 over 2 is 2 to the power of 2. And then on the right-hand side is half plus half p, and downstairs is half minus half p, okay? And then if we compute it, we can obtain that 4 minus 4p equals to 1 plus p, right? We multiply this guy to the left-hand side and then times 2 on both sides, we can get this formula, right? And clearly from here we can see p equals to 3 over 5. Okay, so this basically means that probability 0, or the probability that x is 0, is 3 over 5, and the probability of 1 is 2 over 5. Okay, great. All right, so now what is left is to compute the capacity here, right? C equals to IXY. And from the class, we know in this case, so basically what we see here is that, so C has to be equals to this guy and this guy, right? Those two are the same, and both of them is the capacity, right? So basically, we can write this guy equals to x is 0, and then y. Okay, so now let's compute this mutual information when x is 0. Okay, and so by definition, this basically equals to this guy log p0 given 0 over p0 plus p10 log p1 given 0 over, so yeah, here we have to be careful, right? So this is better to write, this is probability y is 0, so this is probability that y is 1, right? Okay, so given that, okay, so clearly this guy is 0, right? Because from 0 can only go to 0, cannot goes to 1, right? Therefore, second term is 0. Okay, so this together is 0. And for the first term, we need to compute this guy, right? So this guy actually, so this is basically equals to what? It's equals to the probability that x is 0, y is 0, plus the probability that x is 1, then y is 0. Okay, so let's compute that. So let's say the probability that x is 0, y is 0 plus okay, so this equals to p0 times p0 given 0 plus p10 oh, here should be, yeah, this should be 1, here should be 0, right? Let's see. Yes, this is correct. So this is probability of 1 multiply probability that this, okay? And P0 we know, right, that is 3/5, and then P00 that is 1, okay? Then we add, so P1 that is 2/5, and then P0 given 1 that is half, right? Okay, so that is 5/4. Okay, great. So now, given that, we can write C equals to, let's take a look, is this guy multiply log this over this, right? And P00 is basically 1, right? So C equals to 1 times log 1/4/5, that is log 5/4, right? If we take a 2 log here, then we have 0.3219 bits, right? That is basically the the capacity of this Z channel, all right? So this is a solution for 7.8. Now let's take a look at 7.9. Okay, so 7.9 is a continuation of 7.8. In this class, so in this problem, so we consider the Z channel as in problem 7.8, and here we assume that we choose a random code, okay, and each code word is a sequence of a fair coin tosses, right? So here basically means that we're going to generate the random code according to a distribution that is half and half, right? Before we know the optimal distribution for this guy is 3/5 and 2/5, right? But now we use a different distribution, right? Therefore, so if we use this random code, clearly we cannot achieve the capacity, right? So now we need to find the maximum rate R such that the probability of this error average over random generated codes tends to 0 as the block length tends to infinity, okay? So let's see how we can we compute this. Okay, so for this problem, so what we have is that the probability that x equal to 0 is half. The probability that x is 1 is also half. Okay, and the channel we consider is the same as before, right? So it's like this, and here is 1, half, and half. Okay, so if we repeat the random coding process, okay, here clearly in order to make the average error goes to 0, then the achievable rate is basically the mutual information, okay, and basically in other words, this problem just asks us to compute the mutual information between x and y, right? So again, if you do not believe it, just go over the procedure of the achievability part of the channel coding theorem, right? You can see that, so we keep px there to derive everything, right? Therefore, now we only need to compute the mutual information between x and y, okay? So in order to compute that, we may need to compute the entropy of y, right? So let's compute the distribution of y now in order to compute the entropy of y, right? So basically, given this, what we can compute is that the probability that y equal to 0 and the probability y equals to 1, so this vector equals to nothing but half, so which is the distribution of x, multiply the transition matrix P, right, with half, 0, half, and here, so what we're going to get, so if we compute that, so we're going to get 3/4 here, and for this guy, what we're going to get is 1/4. Okay, very good. So this is a distribution of y, and given that, we could compute the mutual information between x and y in this case. So this is hy minus hy given x, okay, and so this equals to hy. So now when we compute this guy, so we have an easier approach, right, which is to fix x and then compute the entropy of y. So this means that we need to do this, x equal to 0, and times the probability that x is 0, which is half, right? And minus another term times half. Okay, very good. And clearly, for the mutual information of y, it's just h 3 over 4, 1 over 4, right? And then when x is 0, y has to be 0, right? So this guy is 0, and then this is the only thing left, right? And for this guy, when x is 1, then there's a half chance to be 0 of y, and there's another half chance of y is 1, right? Therefore, this is nothing but half multiply a entropy of the vector half and half. Okay, and yeah, and we're almost done, right? So the next step is to compute the value of it. So now let's compute it. So for the first one, so this is negative 3 over 4 log 3 over 4 minus 1 over 4 log 1 over 4 minus, so we know this entropy is 1, so this is half. Okay, and if you compute it, you're gonna get this guy equals to 3 over 2 minus 3 over 4 log 3. Okay, and if we compute the numerical value of it, this equals to 0.3113 bits. Okay, and compared to this guy we get clearly, so it's a smaller number, right? So it's less than the capacity. Okay, very good. Okay, so let's see the next question. Next question is our question 7.11. So this is called time varying channel. Okay, so we consider a time varying DMC channel, DMC. Okay, and here consider all the y's can be conditionally independent given x, right? Which is basically means this formula. Okay, and now we let this is the input random variable vector and the output random variable vector. So now I want to find this guy. So which is the capacity of this channel? Okay, so let's see how we can compute it. So what we're going to do is that, so this is a bit kind of like very similar to the approach that we're using in class, right? After we're getting this mutual information, right? Okay, so okay, so in order to solve this problem, so what we're going to do is that we're going to using the same approach as given in class. Okay, so to remember in class when we derive channel capacity, so there's a point that we get mutual information between x, the mutual information between the vector of x and the vector of y, right? Okay, in other words, this basically means that, so we get this at some point, right? But because it's not, it's not, so it is a time varying channel now, right? So we need to process it in a slight different way. Okay. Okay, here is the same as what we obtained in class, right? Nothing different. So here again, so we're going to use the chain rule of entropy, right? So remember that the goal here is to sort of get some mutual information terms, right? Okay, is y minus 1 and xn. Okay, so now because of the memoryless property, okay, so yi only depends on xi, right? So this equals to yi given xi. All right. Okay, again, next step is to break the first term into the summation of the entropy. Okay, and this is nothing but Okay, so now let's see the channel here. So the channel here is basically a EMC channel. Okay, so the capacity, so here this is the mutual information term, right? And the capacity of EMC is nothing but 1 minus H2 pi. Okay. Okay, great. And so note that, so here we have one inequality term here, right? So for this, yeah, so here is also a inequality, right? Because this is the capacity, okay? So actually, both equality will hold if all the x's follow a Bernoulli distribution with probability of half. Okay, you can double check that. So if that is true, then so we have equality here and here. Okay, and in this case, we can get capacity here, right? Therefore, the maximize this guy xn yn over px, so that equals to 1 minus h2 pi. Okay. Next, let's take a look at problem 7.12. Yeah, this is an interesting problem. It's called unused symbol, right? So it asks you to show the capacity of the channel with probability transition matrix given by this guy. It's achieved by the distribution that places 0 probability on one of the input symbols. What is the capacity of this channel? Give an intuition reason why the letter is not used, right? Let's see how we can solve this problem. Okay, first of all, let's write down this probability transition matrix. 7.12. Okay, so the probability transition matrix is given by here, right? Let's label 0, 1, 2 here. Okay, that is 2 over 3, 1 over 3, 0, 1 over 3, 1 over 3, 1 over 3, 0, 1 over 3, and 2 over 3. Okay, so now you may guess which symbol may not be needed, right? Because it's pretty symmetric. There's only one symbol that is different compared to others, right? Okay, so basically, the only thing we need to do here is to compute the capacity of this channel, right? In order to compute the capacity, as usual, we need a distribution of y. Okay, let us assume that the PMF of x is P0, P1, P2, right, for simplicity, because we're going to write a lot of this. And then let's write down the distribution of y. For b of y equal to 0 is basically we use this guy multiply this column, right? So that is 2 over 3 times p naught plus 1 over 3 times p1. Okay, next, the probability that y is 1 is nothing but 1 over 3 times p0 plus p1 plus p2, right? Because here are uniform, right? And this means that no matter what p0, p1, p3 is, right, this guy will be equals to 1 over 3, right? Because this summation is 1, okay? So now let's say p y equals to 2 equals to 1/3 times p1 plus 2/3 times p2. Okay, great. So therefore, we can write the entropy of y in this way, right? So inside we're going to write the probability PMF vector, right, which is basically this guy. Okay, and the second one is 1/3. The last one is this. Okay, so this is the entropy of y, and in order to compute mutual information, we also need to compute this guy. right? Okay, the entropy of y given x, right? So now we're gonna use this formula, right? So we can use the probability that x equals 0, which is p0 times y given x is 0 plus p1 given x is 1 plus p2 given x is 2. Okay, therefore we can get, so p0 is, so we'll just keep p0 here, and then so when x is 0, and then this is entropy of y, right? Entropy of y is entropy of this random vector, right? This probability vector. So that is the entropy of 3 over 2 and 1 over 3. Okay, and then next, so p1 times, so here is basically 1, right? Just sorry, here is basically, it's all the same, right? Therefore it is log 3, right? Okay, and p1 is times entropy of this guy, right? It's 1/3 times 2/3, which is, we can also write in this way, right? We can see that this guy and this guy are identical. Then this equals to p0 plus p1 times this entropy plus p1 log 3. Okay, great. So now we have all the ingredients to compute the mutual information, right? Let's do that. So the mutual information equals to nothing but this minus this. Okay, so now let's copy everything inside here, right? So we can get h of y basically equals to this guy, right? Let's just write down this guy, memorize it, and then you can see this guy is 2 over 3 p0 plus 1 over 3 p1 1/3, and 1 over 3 p1 plus 2 over 3 p2. Okay, and then we need to minus p0 plus p2 entropy, okay, minus p1 log 3. Okay, very good. Okay, so one thing we observed is that, so p1, p0, p2, they are dependent, right? So we know that, so p0 plus p1 plus p2 is 0 right now. So let's get rid of one variable and see what is going on here, right? So what we're going to do is that we're going to replace p1 by 1 minus p0 minus p2. Okay, the reason is that, so here we have to p0 plus p2, right? It's kind of like together, right? So we just replace this guy. Okay, it's sort of like that. Okay, so in this way, so what we can get is that, so p0 have to stay there, plus third p1 equals to 1 minus p0 minus p2, right? And 1/3 and 1/3. p1 is 1 minus p0 minus p2, okay, plus this guy, okay, then minus 1 minus p0 minus p2 and minus oh sorry, so this, yeah, this is not changed, right? So this is a mistake. Here should be p0 plus p2, and so this guy has to be replaced, right? So this is 1 minus p0 minus p2 log 3. Okay, so now let's compute it. So because, so there's some term that could be combined here, right? So actually for the first one, this is 1/3 plus 1/3 p0 minus p2. Okay, last term is 1/3 minus 1/3 p0 minus p2. Okay, so if you compute it, you can see we can get this guy here and this guy here. Okay, and then next step is that we're gonna keep this term. Okay. Minus 0 minus p2. Okay. Okay, great. We can see that, so there's a way to maximize this guy here, right? So this form is kind of clear. So if every item here is 1/3, then this guy will be maximized, right? So that will be less than or equal to, so h 1/3, 1/3, 1/3, okay? And so the equality will hold, okay? When P2 equals to P0 equals to P2, right? So basically this term disappears, then that'll equal, okay? And know that by letting this, it will not affect the later terms here, right? Because so if we have an optimal value for T0 plus P2 here, right, we can always make them equal, okay? So it doesn't matter for the second term. So in fact here, maybe the best way is to replace them back, right? Here, we want to represent everything in terms of these two variables. And now, since we do not have P0 and P2 anymore up to here, right? So we replace it back by using 1 minus P1. So that is maybe more clear, right? To see the relationship, okay? Minus P1 log 3, okay? And so this is 1, this is log 3, clearly, right? Therefore, we can get is log 3 minus 1 minus P1, this guy minus P1 log 3, right? If we combine everything, we can get this log 3 minus, okay? So now it's very clear, right? So this guy will be maximized by let P1 is 0, okay? And then we get log 3 minus, okay? And this is how I solve the problem, you can see, right? Okay, great. So we can see that this is the capacity, right, basically, and that will be achieved, let's say, equality holds when P1 equal to 0. Okay, so it basically means that we do not transmit the variable 1, right? Which kind of makes sense, right? Because the variable 1 corresponding to this and this, right? So this is basically the most special one, right? And mathematically, can you explain that? Before doing that, so let's compute the capacity here, right? So basically, let's compute this guy, right? So basically, you can easily compute this guy as, so that equals to log 3 minus 2 over 3, right? Basically, in the end, we're gonna get 2 over 3 bits, right? That is basically the channel capacity. Okay, so now let's explain what happened for the first symbol, right? For the symbol 1. Okay, so here we could compute the entropy of this guy, hy given x is 1, or the mutual information, right? The same. So this guy actually, as we said, right, if x is 1, then this is what we're gonna get for the output, right? If x is 1, so the distribution of y is uniform. This basically means that this conditional entropy is nothing but log 3, right? So what does that mean, right? y has only 3 possible symbols, right? The entropy of this is log 3, right? Basically, it means that it is maximized, right? So that is the cardinality bound, okay? So this means that if we know by observing, if we use x, then the uncertainty of y is maximized, right? Which is not what we want, right? Or if we compute the mutual information between x and y under the condition that x is 1, then that will be minimized, right? So this is really not that we want, okay? So given that, so intuitively we should get rid of this symbol, okay? However, so that is not the only thing that we want to check, right? So that is not enough. The other thing we want to make sure is that when we derive this guy, okay, so what we want here is the uniform distribution of y, okay? So in this case, it's kind of lucky if we do not use P1, so the uniform of this symbol of y can also be achieved, right? So if that is not the case, then we cannot do that anymore, right? Here, the only thing we need is P0 equals to P2, right? So if P1 is 0, it does not matter, okay? But if it matters, then we still cannot get rid of P1, okay? Or the first symbol 1, okay? So yeah, this maximize the entropy is one reason, and the other reason is that we also need to make sure that without using this symbol, y can also follow a uniform distribution, okay? This is achievable, okay? Then we'll be fine, okay? Very good. So now let's take a look at our next question. Our next question is 7.20, okay? Okay, great. Let's take a look at this problem. So this problem, it is called channel with 2 independent looks at y, okay? So this means that we have y1 and y2, 2 random variable, right? So that are conditionally independent and conditionally identically distributed given x, okay? So now we're gonna show this mutual information equals to that, and then we're gonna conclude that the capacity of this channel is less than the capacity of twice of this channel, okay? Which is kind of obvious from here, okay? So let's see how we can show that. 720, okay, for the part A. So now we only need to show this identity here, okay? So that is relatively straightforward. So x, y1, y2, right? And so we'll just manipulate according to our goal here, right? Our goal is that we have some x between y1 and y1, the mutual information between y1 and y2. And this is a mutual information. Here should be a semicolon instead of a comma. Okay, very good. Okay, so as usual, so what we do is that we're gonna write it this way: y1, y2 minus h y1, y2 given x, right? Here the reason might be that we need the mutual information between y1 and y2, right? In this way, it might be easier to get that. Okay, so the next step is, so we're gonna use a chain rule to expand the first one to get hy1 plus hy2 given y1. Okay. Okay, and then we're gonna expand the second term as well, because given x, y1 and y2 are conditionally independent. So we're gonna get y1 given x and minus y2 given x. Okay, very good. And now let's see what we are getting here, right? So basically we have a y1 and we have a y1 given x. So this two term is already the mutual information between x and y1, right? This is good. So from these two terms, we get mutual information between x and y1, right? That is very good. And now here we have y2 given x, right? So and remember that, so y1 and y2 given x are not only independent, they are identically distributed, right? So this is somehow, so if we can get one entropy here of y2, and then we can get another mutual information here, right? So basically here what we want is nothing but we want to add a hy2 minus, right? This is what we want to add, and then we need to subtract this term here, right? And then copy that here, okay? And then here, clearly this guy will give us another mutual information. And again, so I mean here should be y, yeah. Again, so the mutual information between x and y1 should be the same as the mutual information between x and y2, right? Because given x, they are identically distributed. So I have 2 here, and then the rest is, so this guy, right? Can you see what that is, right? If you take the negative sign out, basically, so this is the negative mutual information between y1 and y2, okay? And we're done, right? So this is basically the first identity that we want to show here. Okay, very good. And for this part B, so what we need to show is that the capacity of this channel is less than the capacity of 2 times this channel, right? So all the tricks come from the maximization operation, right? So let's write down. Let's write the second one as C2, right? Let's write this capacity, the twice. I mean this as C2, right? This capacity of this channel, okay? And 2 times, I mean, we denote this capacity as C1, right? Okay, so if that is the case, we can see that C2 equals to maximization over Px y1 and y2. And from part A, we show that this equals to 2 times this guy minus y2, right? Clearly, this is bigger than or equal to 0. Then this is less than or equal to max. Okay, all right, and now this is equals to 2 right? And directly, this is 2 times C1, right? There's no any, it turns out there's no any trick about the maximization here, right? Because there's only one variable of x, okay? So that is pretty straightforward, and we're done. All right, okay, so now let's take a look at the last problem, so which is 7.35, here. Okay, so this problem is that suppose the channel has a channel P, right? This guy have capacity of C, and then what is the capacity of this kind of channel, right? We have one more item here, okay? And for part B, we need to generalize it to this case where there is an identity matrix, right? IK is the identity matrix, okay? Very good. So let's see what should we do here. Okay, so now let's recall a little bit about our problem 7.5. Okay, so here, so this 7.5 basically means that, so if we consider kind of 2 independent channel, right? So which means that the channel transition matrix is something like that, which is the case that in the question 7.35, right? So in this case, basically what we're going to get is that the resultant channel capacity is the summation of these 2 channels, Okay, so this is exactly what we're considering here. Okay, so basically, let's write it down from problem 7.5. Okay, we know that if we send messages using two independent channels in parallel, then C equals to C1 plus C2, right? So in this case, right, so now our P tilde basically equals to P 0, 0, and 1, right? And we can view this as two channels. One is this channel, the other is this channel, right? They do not, now here is 0, here is 0, right? So they are independent, right? Okay, so a satisfied condition is problem 7.5, okay? So we know that the capacity of P is basically C, okay? And so what does it mean, right? So how can we think about this problem? So the capacity C basically means that we can transmit 2 to the power of C symbols for a channel use, right? So this means that there could be 2 to the power of C symbols being transmitted, okay? And so this 1 bit, or let's say this channel, so what does this 1 mean here? Okay, this means that if we have an input symbol, then we have another output symbol which is identical with this input symbol without error, right? Okay, so this basically means that this guy only add one more symbol, okay? So this basically means that, so the capacity of P tilde is C tilde equals to log 2 to the power of C, add 1 symbol, okay, and then it will take a log. So that will be the capacity, okay? So, all right, and next for part B, so it's almost identical here. So in part B, it says that P hat, okay, let's take a look. Okay, so here's P hat, right? So the P hat equals to P 0, 0, and here is an identity matrix. Okay, so we can repeat this one by one. We'll add another one, and so on, right? Therefore, let's say this is obvious, similar to part A, and the capacity here is that log 2C. So now we can transmit K more symbols, right? You just add the K here. So that will be the capacity, okay? Okay, good. So this is the end of our homework 3, and please take a look and let me know if you have any questions or comments, right? Please stay safe and healthy. So I'll see you next time. Bye.